All right, why don't we get started? My name is Dean Wampler, and I'm going to host the track today as well as do the first talk. And I want to talk a little bit about the talks we've got lined up today. Well, I'll tell you what I'm going to talk about in a minute, but after me, Stefan Karpinski is going to talk about Julia, which is a really interesting new language that tries to modernize data-centric languages. Like if you've ever used R, maybe the Python math libraries, that kind of stuff, then Julia is trying to aim at that market in the same way that, say, Scala is the successor to Java, that kind of thing. Pretty exciting work there. Then Cliff Click, who is kind of famous for his work on the JVM, hotspot, and so forth, is now working on a database system, and he's going to talk about an API for distributed computing. Let's see, I think after lunch, we're going to have Simon Wilnauer is going to talk about Elasticsearch, which of course is one of the important subcategories of big data that I'll briefly mention this morning. Jessica Kerr is a really fun speaker to listen to. She's a friend of mine from St. Louis in the United States, and she's going to talk about sort of how working with data affects your code, the kind of work you do, and kind of related to what was discussed in the keynotes as well. Then we'll have Mark Needham exploring Neo4j, Clojure, these sort of graph computing with examples from like football. I think he means, I'm not sure if he means like real football or hand egg that we call football in the US, if you've heard that joke before. Anyway, all right, so let's get started. I hope you'll enjoy the day, whether you're here or in one of the other sessions. So I'm going to talk a little bit about what's ahead for big data. You can actually grab the slides right now at that last link, polyglotprogramming.com/talks, and if read ahead, decide if you want to leave or not, that's okay. And you can spam me at these addresses. Just briefly, what am I? I bet this is now dead. Okay, yes. I work for TypeSafe, which is a Scala and now reactive stack kind of company. I just joined them recently. Before that, I was basically doing big data for the last several years, mostly in the Hadoop space. I'm a co-organizer of the Hadoop group in Chicago, where I live. I think all these photos are from Chicago. And also, I founded the Chicago user group. And then I've written a few books, two of which on the left need to be updated because they're rapidly growing out of date. All right, enough about me. Let's talk about big data. So here's a couple definitions. Big data is anything which crash Excel, or maybe small data is when fit in RAM. Big data is when not fit in RAM. Maybe a better definition, and I'll let you do the math on the right to make sure it's correct, but maybe another definition, which is really better, is that it's a buzzword, right? And I actually don't like the word very much because not everybody has truly big data like Twitter or Facebook scale, but essentially, it's data that's kind of stretching the limits of what we can do with traditional tooling, whether it's by size or by cost, and so people are looking for alternatives. And as far as data goes, and so I'm going to try to build up a little bit with sort of foundation about where we're at and what we have to do differently to address data-centric computing. Computing has always been data-centric to some degree, of course, but now it's even more so than ever. That's driving, so there's trends in the industry, that's driving architecture choices. That'll take us up to what people are using today, what's wrong with what you're using today, and some of the things that are happening as we're going forward to better address our problems. So I see three trends right now happening, just to frame the discussion. The first one is obvious. This was mentioned in the keynote by Francesco, that data sizes are growing. People are collecting more data. They're saving more data that they previously thought was not useful, and now reassessing that. Like, for example, you can get a lot of useful information out of just server log data about doing diagnostics, predictive analytics. A really interesting application I was loosely involved with in consulting a few years ago was storage area network devices send data back home constantly. And it's a lot of diagnostic data. And what they're starting to do is predictive modeling of that data to look for indications that something's about to fail on the device, send the service guy out there to service it before it fails so the customer never sees any downtime other than the quick turnaround time for the service call. So a lot of data is growing, but an interesting trend is that we're sort of de-emphasizing schemas a little bit. So we're pulling in all of these different sources from raw text, like I want to do text mining on twits, well, twits who are tweeting, let's put it that way, I want to, on the other hand, maybe pull in traditionally structured data or semi-structured data, which is like log data. You know, it always starts with like a timestamp and a server name and a severity, and then you get this noise at the end that's the actual message, so it's kind of semi-structured. Another cool trend, I think, is that we're starting to realize that building models of the world in our code is not very scalable and not very flexible. It's actually better to work with fundamental algorithms and let the data drive the behavior. And one of my favorite examples is self-driving cars. This is the second generation of Stanley, the Google self-driving car that's driven several 100,000 miles around the western US. Apparently, they've only had one accident with these things, and that was when a grad student was driving at the time. So, and actually, you know, the guy, Sebastian Troon, who's sort of behind this project, a Stanford professor, is really very passionate about the idea that a lot of the fatalities on the roads could be solved if the cars just drove themselves. So. But anyway, it's the idea of these fundamental algorithms that drive data. And another very interesting example of this is a little feud that erupted not long ago between the famous linguist Noam Chomsky, you know, who built these very sophisticated models of grammar and language, and Peter Norvig, an AI, who actually runs Google's research group, a famous AI researcher, who is very much on the side of probabilistic models. Rather than building these, you know, all-encompassing models of the world, let basic probabilistic behavior figure out what that next word is in the sentence, or how to translate Chinese to German or whatever. And so this is a great blog post to read. If you actually get the slides and click the link, it'll take you to this post. But it's a good example, though, of the sort of fundamental rethinking of what's the most effective way to work with certain kinds of data like human language. And it really turns out that probabilistic methods are the most effective and successful of all the examples we have, whereas the modeling of grammar in the Noam Chomsky style is maybe less effective. And it may be that our brains are actually working more probabilistically than anything else. But anyway, this drives architecture choices. And briefly, I want to talk about how we used to architect things and how we have to change that. So it used to be that we would basically build object models, our big model of the world in memory, try to represent the domain in memory, as it were. And you know, at some point in the life cycle of the application, somebody would trigger a query to the database. You know, maybe they would log into their account, and you had to fetch, you know, their account data. And that would go through some object relational mapping API, because we all hate working with database people. We hate working with relational databases, so we very quickly wanted to get that data into our pretty little object model, right? We've all been there. Let's be honest with ourselves. So then we have this object model, and we do some hacking on it, and then eventually send it up to, you know, the browser or whatever. The problem with that is it actually is very inefficient to go through all of those layers and building up all that internal representation. Really what we should be doing is embracing the fact that we're pulling fundamental collections out of our databases, and that's true of the NoSQL databases as well as really relational databases. Just embrace the suck is sort of a US Army term, which we've put them through a lot in the last decade. Won't go there, but anyway. And then just, you know, work with this data in a very functional way. And one of the actually interesting implications of this is that we can make our code a lot more agnostic about the world. It doesn't have to know everything about you as a, you know, customer with a payroll, with a HR application or whatever. It can just work with numbers in a very generic sense, and that makes it more flexible and adaptable as we evolve the systems, going back to what I said about data-driven programs. And it turns out this is a much more scalable approach too, but basically we need to start focusing on our fundamental collections and the combinator operators we have on them and so forth, like our flat maps and filters and whatnot, rather than reinventing the wheel for every kind of object we declare. All of us have seen code like this. It's almost inevitable. In pretty much every Java enterprise app I've ever seen was just a big ball of mud, because when you have a domain model of the world, it's really hard to tease it apart into reusable smaller pieces that you can actually distribute remotely. So inevitably, everything goes through this one big wad of Java, even if it's only going through a slice of the actual behavior. Whereas if we do things in the more agnostic functional way, we can, you know, split things to the side easier. We can have focused processes that are scaled in different ways from other processes depending on their load. And that supports, you know, all of these trends that we've been talking about, where You know, I can scale up by scaling out for handling big data sizes. These processes are more agnostic about the world, and that lets us, you know, de-emphasize having to have the precise model that, of course, is going to be obsolete in 2 weeks anyway. And then we can drive these programs more easily with data and let the behavior emerge from the interaction of data and core algorithms. So today, this is how we pretty much do it. It's at least at large scale, or what we think is large scale. You know, I've certainly worked with clients who thought they had big data but really didn't. They could have used some more boring, less hip or whatever technologies, but instead they wanted to build out big Hadoop clusters because they like spending money on hardware. We'll talk about why that's a problem shortly. But anyway, so but nevertheless, at least at a conceptual level, and truly at a practical level too, it does support this model of a very generic compute model that lets us scale horizontally so that we can take a big job of, you know, hundreds of terabytes of data, distribute the computing over a cluster of processing nodes, and then, you know, do our work in parallel, and hence faster. And then underneath is typically a distributed file system or some semblance thereof, maybe a database like Cassandra or whatever. Now, an interesting side note, of course, is that we've seen people embrace JavaScript as the top to soup to nuts, turtles all the way down, top to bottom, whatever metaphor you like, approach to programming, where we might be using Node for essentially our business logic in the middle, using a JSON-oriented document database like Mongo at the bottom, and then of course this all got started because we realized, or Douglas Crockford realized, that we had this nice data interchange format called JSON. So that's a very interesting trend too. I have a walkthrough of what MapReduce is, but I'm actually just going to gloss through it quickly for time's sake because I wrote, as usual, way too many slides. And I'm kind of assuming most of you have sort of know what MapReduce is, but you can get the slides and go through the details if you want. This is one of the most cool sculptures that I know of in Chicago called the Bean. And that's my brother right there with the sort of the drool coming down the side of his mouth. Anyway, this is obviously the platform people are using. It's open source, right? So it's free, of course, except for the hardware. And just quickly, you know, there is a cluster that basically has two big pieces. It has a file system that's virtualized over a bunch of servers, over a bunch of just raw hard drives. And then it's got a job management execution framework on the top, which is doing this MapReduce algorithm, and so forth. The example that I have the slides for that I just want to sketch through very quickly is the inverted index algorithm. So this is the case where, say I have all of Wikipedia, and I want to find all the words in all the pages of Wikipedia. So when someone searches for the word Hadoop, I know which page to take them to. You know exactly what you do with Elasticsearch, or what Google got to be billionaires doing with their version of this algorithm. So you'll have something that crawls the interwebs outside of Hadoop, you know, finds all these documents, loads them in some data store that could just be a flat file even, that has essentially, you know, like a two-column record of here's the document and here's the text of that file. And then the Hadoop part comes in by basically splitting up the processing of all of these documents into separate so-called map tasks. These would be separate JVM tasks in the Hadoop case. And all these things are going to do is they're going to tokenize that text. They're going to keep track of the document. They're going to write out key value pairs. I'm really going fast through this just for time. But the key value pairs will have the key as the word, and each word that's found, and then the document where it was found, and the count, because you'd like to, you know, keep track of which ones are really obsessed with Hadoop versus pages that mention it in passing to provide more relevant search results. And then, you know, it may be that 10 different documents and 10 different map tasks mention Hadoop, so you want to shuffle all those together, and so that when you write the final output, which is that inverted index, you've got words, and then you've got all the documents and the frequencies in those documents that mention those words. And now you could take this, put it on a database for rapid retrieval when someone does a search for the word Hadoop, or one of these other terms I used from the MapReduce framework. And I realize the print's a little small for those of you in the back. Again, this is just better to study on your own. But just briefly, this is really all there is to a MapReduce job. It's both great in its simplicity and horrible. As we'll see, it makes it really difficult to actually use in practice. where you have this so-called map phase that's taking one input and multiple outputs, which should make your ears ring a little bit if you're a functional programmer. That's what mapping is not. It's always one-to-one, yet we're doing zero to many, or one-to-many. Well, actually, we're doing flat mapping. And then the reducing is where we collect these multiple inputs that came out of the map tasks and write our final outputs. Now, I did go through that pretty quickly, but here's a pop quiz. So does this make sense? You know, a MapReduce job without a reducer, this picture. These are the mufflers at the bottom, or the tailpipes. All right, anyway. So really, MapReduce is just a mashup of our old friends, FlatMap and Reduce, and it should have been called FlatMapReduce, but I guess maybe that wasn't sexy enough or something. But. All right, so, but this is our best tool right now, you know, that people are using. It is production tested. It's, you know, Facebook, Francesco mentioned that Facebook has like 700 petabytes of data in Hadoop clusters, so it does actually work, but it's obviously, in my view, a first-generation technology. So there's much to criticize about it. This is my gratuitous beach romantic scene from Chicago in February 2 years ago. That's the frozen Lake Michigan. There's this beach is not far from where I live. Anyway. So we have this distributed file system that doesn't quite meet all our storage needs, and we have this compute model that it turns out to be hard to work with and inefficient. Namely, it's actually hard to implement a lot of algorithms in MapReduce. And the reason for that is that it's a very coarse-grained sledgehammer approach to computation. Instead of having like fine-grained combinators that you're gluing together, if you know what that means, you know, little bits of computation, sort of like Legos, you have these big things, this big map step that's going to read chunks of hard drives into memory, and this big reduce step. And it's actually non-trivial to translate most algorithms that conceptually might make sense, like something like a secondary sort, where I want to do a select statement in SQL, and I want to sort by the date ascending and the last name descending. That's actually incredibly hard to write in MapReduce. It's non-trivial. And in order to do it, a lot of times, because we only get one map and one reduce phase, we have to do it in sequences of MapReduce jobs. And the problem with that is the way this is all implemented is it's going to write the entire data set to disk between those MapReduce jobs, even if it's about to turn around and read it all back into memory. So it turns out it's actually, it's like shooting fish in a barrel, if you've ever heard that expression, to actually do better than this. And some of the alternatives we'll talk about typically get order, you know, 1 or 2 orders of magnitude faster performance just for that reason. Another issue that turns out to be increasingly a problem is that it's very much a batch mode system where I've collected all this data. You know, I walk the interwebs. I've got all these documents and their contents, and now I want to build up the search index. But that's no good if I want to have reactivity on an event basis. You know, if I'm building reactive apps and I want to respond to each event, then that just doesn't work. And Hadoop is very poorly designed for this problem. So we have to find alternatives for that. And the last thing I'll mention right now as a problem is that the Java API is particularly ugly. And I'll show you a beautiful example of ugly here in a second. So we'd like to fix that. So let's actually look at code. We're all developers, right? We love looking at code. And what I'm going to show you is a slightly simpler algorithm than the one that we just talked through very fast, called word count. This is the classic hello world of Hadoop. It's always the first one people write, because all we want to do is basically the same sort of thing. We're going to read in all of those documents and tokenize them, but we're going to forget the documents. We're just going to count the words. We want to find them all and count them. And to do that in the Java Hadoop API, you write code like this, which is deliberately too small to read. And this isn't all of it. I left out the main routine that sacrifices the goats to the cluster, you know, to achieve good results and that sort of thing. One of the things I would like you to notice as we go through code examples here is the colors. And they don't quite show up as well as I wish they did, but they'll look better when we get to smaller code examples. But the green is type. So this is Java, so it's, you know, high ceremony typing. And the yellows are actually doing the work. Those are the functions or methods that are doing real work. And what we would like to get to the point of just relatively little green and lots of yellow. That's really what we want. Right now, where it's mostly green ceremony and not much yellow. Actually, just for, because you're reading carefully what you're seeing here, this is actually the interesting bits that's doing the algorithm. The rest of it is just pure ceremony. when I first saw code like this, my first thought was that 2000 called and it wants its EJBs back. Really, to me, this is exactly what was wrong with the EJB API. It was very invasive. You couldn't write code that was generic and it was sort of agnostic to the infrastructure. You had to just inject all of this stuff into the code and force fit your algorithm to the framework. And that's, of course, a terrible way to write code. The Spring framework solved that problem for the Java community by showing us a better way than EJBs. And I think there's better ways coming, and we'll see examples for writing MapReduce, or not necessarily MapReduce jobs. Well, we're going to see both. If you have to work with MapReduce, what's the better way to write these applications? And what can we do outside of MapReduce to get better performance and better configurability and so forth? Well, the first example for just getting better at writing MapReduce jobs, this is a Fermilab's cool building. Fermilab is sort of like a baby CERN for you Europeans. Anyway, so here's a Java API that at least gives us a higher level of abstraction and hides lots of the infrastructure. And the metaphors in cascading are we're going to build up a data flow of pipes that will glue together. There's going to be some tap that's a source of data. That's, basically our files in this case. And a sink is where we're going to write it, and it's all going to be on HDFS, the Hadoop distributed file system. Technically, cascading doesn't require Hadoop. In fact, it's nice that you can actually run in a local mode outside of a cluster for testing. And eventually, they're going to support other back-end runtimes. But for right now, it's primarily a Hadoop API. And what we really, if you think about what you would have to do word count, we're going to have to tokenize each line of text by word, maybe with a regular expression or something more or less sophisticated. If we were doing this in SQL, and in fact we're going to do this in SQL in a little bit, you would do a group by operation to join together all of the occurrences of a given word, and then you could count the size of each group, and you're done. Well, you have to write it out, of course. So it's really a simple algorithm, and all that the ceremony we just went through is horrible. Well, this doesn't look much better, but actually it is a lot better. For one thing, I'm showing you the whole program. I didn't leave off another 50% for the main routine. I did leave off a few import statements, but I hope you'll forgive me for that. Let me just, I think this will zoom in. Yeah. So just briefly, though, there's still a lot of green because this is Java, but it turns out some of this green, these are actually functions in the pre-Java 8 nasty way of using anonymous inner types for actual just functions. So we've got like something that does basically a for each, and here's a group by operation that you would just use on your collections API in a real language. We're counting things, we're iterating again over things. So a lot of these green types are really just functional abstractions. And we have, here's, pipelines and taps and stuff. So in fact, even though this code looks about as bad as the other at first glance, it's actually much more appropriately leveled in terms of abstractions and hiding complexity and so forth. But we can do a lot better. So Twitter wrote this API called Scalding that sits on top of cascading. Unfortunately, it's a hard word to Google because you get all kinds of sad web pages about people who've been burnt. But if you Google Twitter Scalding, you'll do pretty well. And here's the same program written in Scalding. And that's the whole thing. And now, if you look at the colors again, Scala does a lot of type inference, not completely, but there's not a whole lot of typing anymore. There's a class and a job that we're running, an argument list. But mostly, we're doing what we really love to do in functional languages is take some collection and then sequence operations or combinators to read it in, do the flat map of converting each line to a word. There's some idiosyncrasies of the API, like this is the name of the input field, that's the name of the output field. But it's actually pretty easy to learn this API and then be productive with it. So that was how we split into words, and then here's our group by operation like we would do in SQL, and we can size the group and then write it out. And that's all there is to it. So I actually think that I could take somebody who's like maybe a SaaS developer. They can sort of code, but they're not really developers, and teach them how to use this API, whereas I'd never try that with Java. In fact, that's actually happened in some cases where large data teams have embraced this. There was an informal survey done by the main data scientist at O'Reilly Publishing, and he found that basically data scientists seem to be gravitating towards Python for all their big data work. which has always been popular, but R is kind of diminishing in popularity. And Scala seems to be growing in popularity among developers. And I think it's because of APIs like this one that Twitter wrote that really make it easy to turn what was a big program into a script. So that's kind of the future, I think, for Hadoop and going beyond Hadoop. And just for completeness, now I am a Scala bigot, but I do actually love lots of languages. Let's look at an equivalent API for Clojure called Haskell that was done by Nathan Mars, and it's even smaller. Now it uses data log style queries, so all of these question mark symbols are the sort of variables that will get filled in as the logic query engine resolves information. I don't really understand this API very well, so I couldn't even explain what's going on here to you. But you can see that if you understand the idioms involved, man, you can write some incredibly concise code to do something that's actually quite powerful and useful. Well, all of this is great. It's running on top of Hadoop. It leverages what we've got today, but it still has all of the legacy issues of Hadoop being batch mode and very inefficient. So there are emerging alternatives, and one of them is a Berkeley project that's now part of Apache called Spark. This is a framework written in Scala. The API is very similar to the Scalding API we looked at, the similar sort of conciseness. There are some interesting differences in how they frame these different computations, but you sort of get the gist, and again, the same body count in terms of types versus functions and so forth. And I'll leave it at that as far as the description, but you can probably, if you know any functional language, you could read this code. Maybe even easier to read this code than just coming at it cold than reading the Scalding code, because there's fewer non-conventional idioms here. But all of our friends like mapping and reducing are here, and it makes it a lot easier to just take the concepts we've all been using with collections and now use them in big data, so to speak. So Spark is a great example, too, of a system that actually was designed with the notion of these small combinators of operations that work together. And they also use very intelligent in-memory caching so that you can sequence non-trivial operations together without flushing to disk. And so, again, like shooting fish in a barrel, you get, typically 10 to 100x performance improvement just by not flushing to disk, for example. Excuse me. And it turns out that, we'll come back to this briefly, but Spark was originally designed for machine learning applications. Those algorithms tend to be iterative, and that's really, really horrible for MapReduce, again, because it wants to do map and reduce and map and reduce. So something that can iterate fast is a huge advantage. Well, so I said earlier that we're kind of de-emphasizing schemas a little bit. That was sort of a lie. I mean, we are, but we aren't. We're actually seeing a resurgence of SQL. And it turns out that, I really didn't respect SQL all that much until I started doing big data. I confess that I felt that way. But I really started to love SQL by doing this, because sometimes when you have a question to ask of data, there's just no faster way than to write a SQL query as far as expressiveness and conciseness. And so it turns out that there's a whole slew of SQL implementations that have emerged, starting with Hive, which Facebook invented for their data analyst people to be able to use Hadoop. And then it's been ported to Spark. That's what the Shark thing is, Impala, and so forth. And we'll talk about these a little bit. But basically, they all use this kind of odd dialect of SQL, to be honest, but they are really designed for big data kind of problem solving. Hive is running on top of MapReduce, so it has all of the latency issues that MapReduce does. If you're used to where your database will give you an answer in like a second, sometimes you'll wait 20 seconds for trivial queries to come back in Hive, because it's firing up the Java gophers, and they're running on their little treadmills and coming back in 20 seconds. Spark is a lot faster because it's running on a faster system, and there's now new emerging replacements for MapReduce, really our first examples of the industry embracing what's coming after MapReduce, which are Impala and Presto, where they've actually replaced the MapReduce backend with customized query engines. So you have this general engine called Spark that could do a lot of different kinds of things, but for a narrower problem of a faster query engine, that's being addressed by these projects. So they basically easily exceed high performance by like 100, a factor of 100. And there is actually an ANSI SQL dialect called lingual that's on top of cascading. I actually really like this project, but I think it was probably too little, too late, and they're probably not going to go anywhere with it, just my editorial opinion. Let's do word count in SQL. This is the Hive dialect of SQL. This actually works. Now, remember, we had to tokenize like a single field into a bunch of fields, and that's a bit tricky with a SQL, but it turns out Hive lets you nest arrays and structures and maps inside records. So it's actually easy to split a line into an array, and then explode basically turns that array into, it does like a pivot, so it turns each of those words into a record. But otherwise, this is pretty conventional SQL. I even created the table up here that's just basically an abstraction on top of the file system. I've got documents in some path in my Hadoop file system. I put this abstraction of a table on top of it, and then I write a query against it to generate a new table called word counts here that where I do the explosion. Here I just split by white space, so it's kind of a stupid splitting. It doesn't handle punctuation, but nonetheless, it gets the idea done. And I group by word and I order by word, so I'll see the most frequently occurring words, at least the way I wrote this one. So this is actually almost about as concise as scalding. And if you've already got the tables created, then you're just writing something like this, which is very fast. I actually think we're in an era that I just call the SQL Strikes Back, because what I've seen going into big enterprises is typically you'll have like a handful of overworked admins, sysops guys, and then you'll have like maybe a team of a couple dozen developers, and then you'll have hundreds of these data analysts that all are programming, SQL and SAS and those kind of tools. And Hadoop would simply not be as popular as it is today if it wasn't for a SQL option, so that they could write queries somewhat like they're used to against this big wad of data. And so I think that Hive has actually made Hadoop the big industry that it is. And if it wasn't for Hive, then it wouldn't be nearly as popular, because it wouldn't be as usable by a wider class of people. And it's interesting to me that now we're seeing a lot of the NoSQL databases start to add query languages. Of course, the document-oriented ones like Mongo have had a query capability for a long time. Although crucially, in Mongo, you can't really do joins. So that's actually turning out to be an issue for some people I know. Whereas Cassandra has actually got a SQL dialect now. And I think this is the right movement, that SQL, despite all of its flaws that we can cite, it's really, really important to typical end users. And even for us developers, a lot of times we'll write a Java program when we could have done 1/10 the work with a SQL query. So I really think we should embrace SQL ourselves. And fortunately, there's actually a new set of databases, let's call them. They're being called NewSQL because people love buzzwords, that are trying to take the lessons we've learned from scaling NoSQL systems, horizontally and whatnot, and bring it back into the relational world. Maybe the most famous example is Google's F1, where they actually have global distributed transactions implemented in this globally distributed database. And of course, they can do badass things like put atomic clocks in their data center, so they can try to do time syncing, over longer than speed of light is obviously going to affect how you synchronize clocks. This is an old problem, but they have the money and the chutzpah, I guess, to actually try and make distributed transactions work globally, in the real definition of global. But some of these others are startups that are also pretty interesting in trying to do this. So what I said earlier about formal schemas are being downgraded in importance, that's partially true. It's certainly true in some problems, in some industries. But SQL, or a model like SQL, is not going away, and we really need to understand that that's kind of the future again for big data. I also mentioned earlier that MapReduce is really oriented towards batch mode processing. It's not at all suitable for real-time event stream handling and so forth. So some alternatives have emerged, and you may have heard of Storm, which is the most popular example. This is another thing that Nathan Mars, who invented Haskell, came up with. Storm is sort of like you call it the event stream version of Hadoop in a way. It's designed from the ground up to be a distributed system to provide some degree of reliable event processing, as opposed to like a single vertical system on one box that has high throughput. And just very briefly, the topology of a storm deployment, they use the term spouts for sources of data. This could be like, logs that are being streamed in, or events that are being triggered by web services or whatever. And then you have different processing stages called bolts that could be anything that you want to do with this data. Filter it, map it, join it even, and maybe write it to other stores. Nathan has a really good book actually called Big Data that he's slowly working on. You may have seen this in, it's a Manning book. And it lays out his vision of how to bring like the Hadoop batch mode world together with the real-time event streaming world to implement non-trivial applications. It's a good read. And other options, Spark has recently done some re-engineering of their system to make it better for real-time event handling. And of course, people have been using event queues forever. Another possibility, though, is to go back to databases. Should we bring those back? This is actually a photo outside my condominium window in Chicago. These heavy lift helicopters are used to bring new air conditioning units to the top of buildings and stuff. So every now and then you wake up on Sunday morning with this whack, 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 whack going on outside your window, and these things are flying down at eye level, or whatever. It's kind of scary, in fact. But nevertheless, could we use databases for event processing? Well, in a lot of cases, it actually does work because they tend to be very good for fast writing. And sometimes all we need to do is capture the events in a database like Cassandra or Mongo. In fact, I did a project like this many years ago with Mongo where we basically used it as a sophisticated logger. And then we had the query API on top of it. So maybe we can write to a database. What about we have this distributed file system I mentioned earlier. Can we use that for this purpose? Well, really, no. It turns out it was also designed for batch mode writing of big chunks of data, not for incrementally adding data to existing files. So it's really not a suitable choice for writing updates. We really need something in the middle, which complicates our architectures if we're using Hadoop. So the trade-offs are Hadoop versus SQL, or even NoSQL. Well, we do get a very flexible compute model, even though it has its limitations. It's really great for batch mode, like scanning table size chunks of data. Whereas if we want to do something that's more transactional or event-driven, something that maybe has more of a predefined schema than a database is often a better choice. Now here's a really common scenario in the Hadoop world, and I've worked with customers on this, where they have a very nice data warehouse appliance, but in order to get beyond the size limitations, they'd have to pop another $1 million or something. And that often sucks. So it turns out Hadoop is emerging as a data warehouse alternative because it's got this SQL capability. I mean, the pros of these data warehouse systems are they do tend to be very mature and have rich capabilities, but they do have size limits. They don't scale as well, especially in a cost per terabyte basis. They tend to be rather expensive. In fact, depending on who you want to believe, the numbers are something like 100 times more expensive per terabyte for certain appliances that I won't name versus Hadoop. Well, SQL is very important for data warehousing because you want to write analytics, and that's what they've been using all these years, so they're not about to give up SQL just to keep doing their traditional back-end analytics. But you don't need transactions, so maybe the batch mode problem with Hadoop isn't an issue so much with warehouses. And in fact, it's turning out that that's kind of the case, where we do get this benefit, but also this disadvantage, these two disadvantages with data warehouses, limited scalability and very expensive cost. Well, we get something that's less mature, but it's actually getting better at doing SQL, and it's very scalable. It's as scalable as any system that we can trust, with hundreds of terabytes to petabytes, and it has a very low cost, relatively speaking. So we're seeing Hadoop as sort of the poor man's data warehouse engine these days. At least that's one of the uses. Okay, so another drawback of MapReduce is that it really sucks at graph algorithms. And the reason is that typically graph algorithms involve traversing the graph where you'd like to be able to step, very small steps. I'm starting at maybe whatever this root node is, and I want to walk the tree to do whatever it is I want to do, whether it's sending messages to neighbors in the graph or do various graph traversal algorithms. And that's not so great if I have this system that really wants to have one big chunk of mapping and one big chunk of reducing. So people are inventing alternatives to this. Ironically, Google started using MapReduce as a way of implementing PageRank, their famous indexing algorithm, as well as other computations. But PageRank is really just, I'm walking the graph of the internet, effectively. And that is really sucky for something like MapReduce. So it wasn't ideal, but you can sort of make it work, and a lot of systems have done that. But again, to clarify, the problem with Hadoop is if I'm walking nodes, then I want to be able to do that in very lightweight steps. I don't want to have to write one MapReduce job per step in the graph traversal. You write all that data back to disk, read it back into memory. It's just really terrible to do that. So how do people get around this? Well, an emerging model of distributed graph computation is bulk synchronous parallel, where it's basically synchronous in the sense that I'm actually doing this stepping in parallel, but each series of steps is done synchronously. So if I start at that one node, I'll step to all the neighbors in parallel, but one step. And then we'll update our state, and then we'll do the next step in sequence and so forth. And Pragal is a Google system that was designed to do this. I hear mixed stories about whether they're actually using this in production. Distributed graph algorithms and traversals and so forth, systems is kind of a research cutting edge thing. So no one's quite figured out what the best way to do it is. But if you're interested in doing this in like the Hadoop world, because you have graph problems, check out Giraffe and Hama. Now what they do, they actually cheat with MapReduce. They don't actually run a MapReduce job for every step in the graph. They just run this long-running MapReduce job where they just use that as a resource manager, and they step internally over the graph data. And then Aurelius Titan is a really interesting new database that sits on top of Cassandra that may turn out to be the best open source alternative for a distributed graph database. Now we're going to have talks in the conference about Neo4j. I didn't mention that because it's more of a single machine database. But it's also, if that's the size of your data, then that's really the much better choice than going with one of these. Okay, to sort of get to the end here, sometimes we need more specialized tools that are built for specific purposes. And we saw a little example of this already with compute engines that are oriented towards queries, like replacing MapReduce to do SQL queries, which is what Impala and Presto are doing. And we're seeing other customizations like particular file formats that are optimized for certain query problems. But a really good example of this trend of focusing on a subdomain of this larger big data problem is really addressing search with custom tooling, because that's such a ubiquitous problem. And pretty much the two open source leaders are Lucene combined with Solr, and then the Elasticsearch project. And this track, as I said earlier, will have an Elasticsearch talk later today. I just wanted to mention this. I won't go into detail, but if you're interested in this topic, come back later today. And then finally, we mentioned that MapReduce kind of sucks for machine learning algorithms because they tend to be highly iterative. So what do we do about that? How do we do machine learning better? And in machine learning, what I mean is things like how could we do better at doing movie recommendations like Netflix, or classifying things like spam versus not spam, or even clustering, like finding groups within social networks. Since this is not a good fit for MapReduce, are there alternatives? Well, once again, it kind of boils down to there are things that run on top of MapReduce that do the best they can, like the Mahout package of machine learning algorithms. Mahout has some really good APIs for like matrix computation, linear algebra, which is very important in machine learning algorithms. There's a system called Pattern that runs on top of cascading. And then Spark is real, if I was really building a machine learning system as opposed to just a general data system, and I wanted to live on the edge a little bit more, I'd probably go with Spark over MapReduce for this reason, that it's going to be much faster. And just to back up a little bit, how would this actually work? Well, typically you would use Hadoop to, in batch mode, train these algorithms, like your spam filter, and then store that data for the filter in some fast database so that at runtime, when people are asking, is this spam or not, you can get a very fast answer for them. And the last thing that I think is really interesting, and it goes back to that debate I mentioned between Norvig and Chomsky, is I think we're going to see emerging tools that make it easier to write these probabilistic models that people use for automatic cars and language analysis, called the Bayesian networks and Markov chains are kind of the buzzwords for the models. These are hard, these really require expertise to write today, and there are actually attempts being made to build languages that make it easy to express these concepts that make them first-class citizens. Okay, so let me wrap up quickly because we're out of time. This is the beach scene again. Well, anyway, so I think Hadoop MapReduce is really kind of the enterprise Java beans of our time, which is good and bad. I mean, just like EJBs in the old days, they got people going. They were a solution to a real problem, but they definitely were the first generation and not the last word. So we're already seeing MapReduce kind of go away because it has a lot of performance issues, and it's being replaced by things that are either functional style languages or APIs like the Scalding and the Spark, or it's SQL that's coming back. And I think that the reason that these like functional language solutions in SQL are so concise and appealing is because basically big data at the end of the day is mathematics. And so functional languages, which are built on the core principles of math, are always going to be our best tools for big data, not object-oriented stuff. But a lot of people have said that concurrency and the need to write scalable horizontal apps is really driving adoption of FP. But I think the next wave is actually going to be driven by data-centric problems, because that's kind of a bigger problem that more people have to be able to implement themselves versus we'll kind of solve the concurrency problem with actor libraries and whatnot. Okay, so we're kind of out of time. I'll just take questions privately afterwards. I don't want to get between you and your coffee, and I hope you enjoyed the rest of the day.